Hello and welcome to Office Hours by BitGardener. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today we're talking on color difference equations. We have our technical applications specialist, Noah Morgan, going to be presenting. A couple things before we get into it. If you're unfamiliar with our Office Hours format, this is usually a shortened presentation. This one today is going to run a little bit longer than we usually do, maybe 25, 30 minutes, just due to the bulk and complexity of the content. Following that, we'll open it up for questions. So if you have any questions, challenges you're experiencing in your own facility, please log them in the chat box located at the bottom right-hand corner of your screen, and we'll get to them. Also, we are recording this, and also through the discussion, the recording will run. So immediately following today's webinar, you'll get a automated message with the link to the webinar. Feel free to listen, watch it again, take screenshots, share it with colleagues, whatever you like. So with that, let me turn things over to Noah. Noah, how are you doing today?
I'm good. Thank you for the introduction.
Excellent.
So like you spoke of before, today we'll talk about elliptical tolerancing and specifically the evolution of color difference equations. All right, so to give everybody some background, so this is the CIE lab system. It's essentially just a way to have coordinates for every color that exists. So if you see, it's a three-dimensional system. We have the L value, which is the lightness. So at 0, it's black, and at 100, it's white. And then on the A-axis, we have negative A, we have a green, so it gets more green, and at positive A, it gets more red. And then on the B-axis, at negative B, it's more blue, and then at positive B, it's more yellow. So we see we have a sample here, a little example. It has an L value of 58, so it's a lighter color. An A value of positive 30, so it's a little more red. And then we have a B value of positive 36, so it's a little more yellow. And with all those coordinates combined, we get a color of orange. And so that's essentially how the system works. And so we want to look at, normally when we're looking at colors, we're looking at the difference. So what that is usually it's the difference between the sample and the standard. So to find that, we have the delta E star, which is the first equation we're going to look at. It was developed in the 1960s, and it's a fairly simple equation that just includes the delta L value, the delta A and the delta B, and then square roots it all. And so what that is you can think of this circle here as the sample, and this circle here is the standard. So we essentially have the delta A. It looks like it moved a little more positive, so it got redder. The delta B, the difference in the B, it moved a little more yellow. And the difference in the lightness moved a little higher, so that it all gets calculated into our total difference, which is our delta E star. And that's essentially just how the delta E works. And so another system usually used for chromatic colors is the LCH system. This is a little different than the LAB system because this includes the hue angle. So we have the H value here, which is that hue angle. It's going to start on the red axis, so that positive A, and this is going to be 0. And as it moves counterclockwise throughout color space, it's going to change. And then we also use the C value, which is chroma, and it starts at 0 and then moves out as the color gets more chromatic or more saturated. And then we also have that L value, which is the same as the lightness scale in the LAB system. So it's just two different ways of figuring out where you are in color space. So with that, I just spoke of before, for chromatic colors, you're going to want to use LCH. Whereas non-chromatic colors, you want to use LAB. And this is because you can get more accurate representations of where you are in color space depending on what type of color you have. So for non-chromatic colors, you want to use LAB when your chroma is less than 10. And then for chromatic colors, if your chroma is greater than 10, you want to use LCH. So with that background, talk a little bit about tolerancing. So this is an example where we have our standard, which is right in the middle here, and we have acceptable matches, so acceptable samples that pass our visual evaluation inside here, and then we have our visually rejected matches. So those are all the little circles with the X's on them. So what we see, this is with the delta E star LAB system, where the circle is what we visually see, and with all these little circles that pass. And this is the calculated tolerance from that equation, is this box here. And what we see is it pretty much works. You know, we see that it separates the good passing samples versus and the failing samples. So circle tolerance agrees well with visual perception. Rectangular tolerance approximate a circle. And then so this is an example of when you have these higher chroma colors, so these more chromatic saturated colors, it's not always going to agree the same as those achromatic colors. So in this case, like the example before, we have a standard in the middle, and these are our passing samples, and we have our failing samples here. And what we see is if we use that box tolerance, like we did before with those achromatic colors, those pastel colors, we're going to be missing a lot of these passing results, these passing samples, and we're going to be getting rid of those, that's a big issue. So what we can do is we can expand that tolerance, but with that delta E mathematical calculation, when we expand that tolerance, it's still going to give us this box shape. And when we do that, now we're introducing these failing samples in here, as well as the passing samples. So we can see now that delta E star isn't the best equation to use in this case. So we see elliptical tolerancing agrees well with a visual perception. Rectangular tolerances don't agree well with the visual perception. So we want to find a way to get this elliptical tolerance, because it matches best with our eyes, because our eyes aren't perfect. They're not going to see exactly how this calculation is wanting it to see. So with that, we have the LCH tolerances for chromatic colors. We can see it creates this more of an elliptical shape here that agrees well with our visual perception instead of the LAB system. So you can see that this is a lot better than before with the squares. So this is just one of the examples of tolerancing and how these different equations and different coordinate systems are better with certain colors and worse with other colors. So looking more into the delta E star equation, we have an example here. We have a standard blue, we have a sample 1, we have a sample 2. So in this sample 1, we have our delta E star equation, and we see across the board both all three values for L, A, and B. The difference is pretty much proportional throughout the entire sample. We end up getting a delta E total value of 1. Whereas sample 2, we see that all the color differences in the A value, but we still get a delta E of 1. Then we find out that this sample 2 looks completely different than sample 1 and the standard, because all of that color difference is focused just on one value. But what would happen is this would theoretically pass as your delta E is less than 1. It would pass, but visually it doesn't pass. So this is one of the issues with using delta E star. So measured deltas do not correlate well with visual impression. And we see here, this is an example of what our eyes are seeing. So this is how our eyes view color. So these circles, you can see there's a lot tighter circles down here in the center rather than out here on the edges. This is because our eyes have tighter tolerances when viewing pastel colors or achromatic colors. But as colors get more chromatic, our tolerance in our eyes is a lot larger. So if you compare like two light grays that are different, our eyes can easily pick up that difference. But if you compare two chromatic reds or two chromatic greens, our eyes are going to have a hard time distinguishing them because that's just the way we see. So visual acceptability is based on ellipses, not circles. Tolerances for hue are tighter than for chroma. So we can detect a difference in hue very easily, whereas in chroma, it's going to be harder for our eyes to detect that difference. Chromatic colors have larger tolerances than pastels or near neutrals. And the size and shape of ellipse changes dependent on the hue. So acceptable color differences vary from color to color. Green has larger tolerances than dark blue, so that's saying that our eyes can easily pick up differences in blue rather than differences in green, because our eyes aren't perfect. And so this is an example. This is just to talk about some of the different equations that exist out there. There's delta E CMC, there's delta E94, and delta E2000. Each one of these came after each other with some time in between, but they all had a goal in mind, a common goal, which was for better agreement with visual color perception. And they wanted to create one tolerance for all colors that would create a uniform color space. So essentially, if you're a company that develops 1,000 colors and you use delta E star, you have to create your own tolerance for each one of those colors that match right, so you're not having failing samples that don't visually match go out and say they pass on the machine. You want one, if you have all these colors that you're creating, you want an easier way to have them all toleranced out instead of having to go into each one of these colors and making your own adjustments. So to look at the first equation, which is delta E CMC, it was developed in 1984, and it was based on the visual evaluation of textile samples. It's currently in the British Standard, American ATCC test methods, and ISO test methods. And it's based on the elliptical, not the rectangular spacing of LCH. So those elliptical shapes that we looked at before. And in this specific equation, it corrects for chroma, hue, and lightness dependent on perception. And this is an example of what that looks like. So it's that elliptical shape, and we have the calculation up here. So we still have the difference in the L, the C, and the H with a couple more factors. It's a lot more complex equation than the original delta E star. So it has a three-dimensional ellipsoid with axes corresponding to hue, chroma, and lightness, and has these weighting factors. So that SL, SC, and SH are dependent on the color of standard. So depending on that color, these weighing factors can change, and that can change what that elliptical is going to look like with the size and the shape. And then you have these application factors, L and C, that modify the lengths of these axes. All right, so moving on to delta E94. It was developed in 1994, but later published in 1995. This one was based off of the evaluation of a new sample set that were solid colors only, so no effect colors. It's currently published in the CIE Technical Report 116 for industrial color difference evaluation. And this is based on the elliptical spacing of delta L, C, and H, but it corrects only for the chroma-dependent perception of chroma and hue. And there's no lightness correction in this equation. So we see here, this is the actual equation here. Somewhat similar to the last equation, but has a couple different factors. So weighing factors SC and SH are dependent on the chroma of the standard. And then we have application factors that are used to correct for variations in different conditions like illumination intensity, background field, your viewing field, and your sample. So it's a little more advanced equation. And so we see here in this example of a brilliant yellow, like a high chromatic yellow. The difference is from using delta E star, where it's that box tolerance, versus delta E94, it's now an elliptical tolerance. And what's nice is that for chromatic colors, we have a larger visual tolerance in chroma than in hue. And so we can make a nice tolerance here that takes into account that chroma and the hue. Here's just another example of how a brilliant red, a high chromatic red, is different than a achromatic red-brown color. So you can see here in delta E94 that tolerance is a little different. We have a high chroma tolerance here versus, because of it's a non-chromatic color, that chroma goes down. So it's a smaller tolerance long-wise, whereas this one's a longer tolerance. And what that does is it's because of that chroma, right? We have a hard time depicting that chroma, or we have a hard time depicting that chroma on high chromatic colors, but on less chromatic colors, we can easily pick up those differences. So this takes that into account.
Hey, Noah, can I interrupt for a moment?
Yep.
We have one question in here, and I think this is timely based on what you're talking about. Can you define chromatic colors versus non-chromatic colors?
Yes. Let me see if there's a slide that can show you.
Maybe I'm jumping ahead.
No, you're fine. So chromatic colors are very saturated colors. So if you see in this example here, the colors on the outside are very, you could say they're saturated colors. They're very bright and vibrant, whereas achromatic colors are colors that are very pastel. Like your light yellows or light reds, they're not going to pop at you. Whereas those chromatic colors like fire engine red, those colors are going to pop at you. And so when I'm talking about these tolerances, it's basically saying that, those bright reds, if we have a bunch of bright reds that are different and they're lined up next to each other, we're going to have a harder time figuring out which ones are different, rather than if we had a bunch of very light reds or, very light yellows or grays, we're going to easily be able to pick out those differences because our eyes are more in tune with those lighter colors. Does that answer the question?
Thank you very much. Larry, if you have any follow-up questions, just jot it in the chat and we'll get to it. But all right, thanks for that explanation. Sorry to derail your presentation.
All right, continuing on. So to the next equation, we have delta E2000. So this was the most recent equation. This one was developed in 2000, but was given out in 2001. And so this one was based off of several already existing data sets, like the ones we spoke of before. It's currently published in the CIE Technical Report 142, and it's based on the elliptical spacing of delta L, C, and H, just like the other equations. And in this one, what's different is it has 5 corrections. So it corrects for lightness, chroma, and hue-dependent perception. But it also introduces this rotation function that improves the performance for blue colors, because we see blue differently than other colors. And it has a factor for rescaling the A star axis for improved performance of gray colors. And so we see here, this is that equation. It's a lot more complex than the other equations because we have this weighted color difference part, and then we also have this rotation function. And you can see here the weighted color difference part, not the regular CIE lab components that are L star, C star, and H star, but they are prime. So we have delta L prime, delta C prime, and delta H prime. So it's a little different. And what that does is you can see in this nice example here, in the blue color space, it was found that our eyes have different tolerancing. So instead of having these, regular circles or regular ellipticals, it's now in this blue color space, we have these tilted ellipticals. And that's basically trying to match exactly how our eyes see. So we can see the interaction between chroma and hue in the blue region from 275 degrees plus or minus 25. So that's this region here that tilts it. So it's main influence for high chroma blue color. So if we have a high chromatic blue color, this is the shape of our visual tolerance rather than the regular visual tolerance for other colors. And so here's an example of that. This is for, say, a darker blue. So in Delta E94, it's the circle shape. You could say this would be considered passing based off of that equation. But when we change it over to Delta E2000, these samples are now failing because they're outside of that tolerance. So if we see visually, this is going to correlate exactly how our eyes see, whereas this is not going to correlate exactly. So if we go back and look at some of these samples, we're going to find there's slight differences that our eyes pick up. So this equation is more accurate than that last equation. And this is just an overview of it again. So the weighted color difference part improves the agreement of the visual color difference perception for neutral colors. And for low chroma colors, the G increases the modified A prime compared to the regular A star. And at high chroma colors, A prime approaches A star. It's just explaining kind of how the calculation works here. All right. That was pretty quick. So with that, if anybody has any questions, feel free to chat it down, and I'll hand it over to you, John.
Yeah, thanks, Noah. Yeah, you got to that a lot quicker than I thought. So good job. Like Noah said, if you have any questions, just jot them down in the chat box. We'll get to them. When it comes to color equations or color difference equations, I know they've, as you walked us through, they've progressed over the years. Do different industries standardize on different equations, or how does that work?
Yes, so different industries will usually use different equations, and it's just what they've been using historically for a long time. Mm-hmm. And so that's an issue because we see now that there's better equations out there that match really better than the previous ones.
Yeah.
But the problem is that these industries they're stuck in the past, essentially. They use Delta E star, and in order to have someone new come in and use a different equation, the entire industry would have to change. So it's a difficult subject to get everybody to switch over. So really, it's all about educating and showing why these equations are better and how it correlates differently.
Right, and so it fits the industry, and I'd say, correct me if I'm wrong. Remember, I'm just marketing guy here, not too technical. But if different people, within either same facility, same plant, just different shifts, if they're using different equations, you're not measuring apples to apples, right? That's going to create a lot of problems.
That's exactly right. So if you use a different equation, you might have passing results, and then you send it off to another location and they're using a different equation. They might have failing results, and then that's when problems arise. My stuff isn't matching your stuff.
Yeah, and it's similar to just having the latest consistent firmware across the board, and really your process mapped out so everyone's using the same equipment, doing the same measurements, in the exact same place and at the right angle. Just because then you're going to get actual accurate data that you can compare and actually measure what you're doing instead of having it a little cloudy.
Right.
Okay, cool. Question here, do all of these systems use the same CIE lab color space?
Yes, so all of these systems are based off of that color space.
Okay.
There used to be a different color space back in the 30s, but CIE, when they developed their color space, so I'll pull it up just to show everybody again.
Yeah.
It was decided that this is the best way to identify colors. So they all essentially follow this now.
Okay. Excellent. Excellent. So, I mean, you talk to people, customers on a daily basis. What are the big challenges or questions they have when it comes to difference equations? And how do you help solve that? Or I guess I'm asking for some tips for our audience on how they can avoid challenges or pitfalls.
Yeah, so some challenges that come up is someone will ask, what equation should I use?
Yeah.
And it's a really loaded question because it really depends on the application, you know, and what's going on with your product. Are you going to ship it out to somebody else for them to use in their product? Because then you have to make sure that both you and where it's going to end up they're using the same equation. Because
Yeah.
if you use a certain equation that passes and they use an equation that fails, you could have those issues. So really, it's all entirely dependent on that application. But if you're making your own products and you're color matching your own products and you want the best visually representative um, difference equation, then I would recommend using Delta E 2000 because you can get the best, visually matching results
Yeah.
compared to these previous difference equations.
Yeah. Yeah. Makes sense. It just comes down to consistency in your process. It seems like everything leads back to that. Another question here. This may be more of an instrumentation question, but does the type of light source a spectrophotometer uses matter for color difference equations?
So it doesn't really matter. Really, the light source, especially these days, is with an equation. So we found that D65 has a certain wavelength, and we can input all that data into the different equations, and it doesn't make a really big difference. Now, if you compare different light sources,
Mm-hmm.
those values together, you're going to get different results. So if you really want to match your results, you want to have the same light source and the same equations.
Hey, that consistency thing again.
Right.
How about that? Another question. I understand the chroma and hue, but can you elaborate further on the lightness, darkness?
Yes. So
Maybe
you can
maybe
see.
just go through all three of them again,
Yeah,
if you don't
absolutely. So
mind.
this is color space. Pull up LCH. So this is a C-Lab system with the color space.
Mm-hmm.
So chroma is basically starting at 0. So think of this rod in the middle. We'll talk about lightness first. So lightness at the very bottom down here is black. It's no color whatsoever. And as you move up the scale, it gets lighter and lighter and lighter and lighter until you get to the top, which is 100. And that's when you have pure white.
Okay.
And you can think of this whole system as being a sphere, but it's hard to show,
Yeah.
visually a sphere color space. But think of the whole system as a sphere. So any color can lie anywhere in the sphere. And chroma is just a line that moves from 0, so that white color, out into more chromatic colors on the outside. And then hue is just that color difference in the hue. So just angles, if that makes sense.
Mm-hmm. Mm-hmm. Yeah, it's hard to not see this as like a true physical sphere. You got to use your imagination a little bit here, but it's
Right.
essentially the more the let me see, is it the more the chroma, the it shifts from a non-chromatic to a chromatic color. Is that an accurate statement?
Exactly. So
Okay.
you can go from a washed red color to a very bright fire engine red color. That's the best
Okay.
way to put it.
Yeah.
Yeah.
Another comment in here. So chroma is sort of like saturation, and hue is whether it's blue versus red, for example.
That's exactly right. So chroma is just more saturation, more vibrant color,
Yep.
whereas hue is just, you go for green to yellow to orange to red. Those are different
Gotcha.
hues.
Gotcha. That makes sense. And I mean, how does this work with, instrumentation, whether it's ours or one of our competitors? Do you set the actual, color equation, in the instrument, or how does that work?
Yeah, so with the newer instruments, everything is divided up mathematically. So
Okay.
you can essentially pick an equation. So say you start with delta E star, and you measure a sample, and then you measure a standard, and you'll get that tolerance,
Yeah.
and it'll tell you if you pass or failed and give you that delta E value.
Okay.
Now, and it's a setting that you can change in the instrument, just which equation you're using. Now, because everything's mathematical with the newer instruments, once you take that value of whatever color you measured, you can then put it into a software and then change the equation on the software after you took the test,
Okay.
and it'll automatically put all the data into the right information for that exact equation. So you can change the equation after the fact or before the fact.
Gotcha. Gotcha. So, I mean, one takeaway I immediately thought of is like, okay, after this webinar, I want to check all my instruments in all my facilities and make sure they're set to a consistent, color equation. That a good starting point?
Yes, that's a great starting point. Then you would have everything on the same page.
Cool. Cool. Another question here. Is white considered all of the colors, white light? And is black considered none of the colors or an absence of color? What's your
Yep,
take?
that's exactly right. So white is technically all of the colors combined into one, whereas
Okay.
black is known as the absence of color. So that's exactly right. Black is no color, white is all the colors combined into one.
Gotcha. Okay. Makes sense. What other, yeah, keep the questions coming, folks. This is great. And if you're experiencing any challenges in your facility, just ping me. I can unmute you from my end or unlock your microphone if you want to elaborate and, just talk about a challenge. We'll keep it anonymous, definitely. So just let me know in the chat and we can do that. We got, some time here. The time is yours, really. I can carry on with Noah, no problem. Yeah, would love more questions, comments from you all. So what else, Noah, when it comes to challenges that you've seen in working with customers, what are typical things that you see people doing that are inaccurate or could be improved?
Well, like I said before, it's keeping everything consistent. I'd say that's number one of the issues I see a lot is,
Yeah.
things aren't consistent. So, I'll get a call from one plant and another plant, and they're saying, we're measuring the same thing, but we're each getting different values.
Yeah.
And so the first question I ask is, what equation are you using?
Yeah.
What light source? These
Yep.
different things that could affect your reading.
Yeah. No, that makes sense. You got another question here from Brent. Is there a good way to account for metallic effect in reading colors with a spectro?
I would have to say no.
Okay.
The reason being is because metallic effect, it's very different. It would need to be measured with a special metallic spectro.
Mhm.
So something that has multiple angles versus just one angle to get the full story of what's going on in that color.
Mm-hmm.
But there's really no good way to just use a regular 45 or D8 spectro and get, account for that metallic effect.
Yeah, you definitely need that multi-angle to pick up the metallics and pearlescence. Gotcha. Cool. Let's see. Okay, so based on previous question, which was, the white being all colors and black being absence of color. On the white black, does the L-axis lightness equal white and the L-axis dark equal black?
Yes. So in this example, that's true. So it's just saying, it starts at 0 and goes up to 100, and it starts at black. So, again, if you think of this whole system as a sphere, all the colors around this area are going to be very dark. And as they get, the L value rises, they're going to get lighter and lighter and lighter until they're at the top. And once it's at the tippy top, all those colors are white.
Yeah,
So,
we're missing your pointer if you're pointing.
oh my bad.
There we go.
Yes. So,
okay.
The lightness at 0. So anything down here in this region is dark. It's a very dark color, whether it be a dark green, a dark red, or a dark yellow, or dark blue. They're all going to be very dark. And as you go up this axis, it's going to get lighter and lighter until you're at the very top up here, which is pure white.
Gotcha.
So any color around here is going to be very light. And it's essentially just like the other axes. So you go from a green to a red, but the L, you go from a dark to a white.
Mm-hmm. Good. How does a D8 measurement versus a 45-0 factor into this?
So D8 is going to, I know we've done some different presentations on that, but essentially they're different measurement techniques. So 45-0 is having a sensor directly overhead with an illumination coming from the side or vice versa. Whereas D8 is using the sphere technology, which is just a white sphere inside the measurement apparatus that's coated in white. And so all the reflectance bounces off of that white sphere and eventually gets put into the sensor. And so those values can change. So I would say if you're ever measuring with any of those instruments, make sure that if you ever compare results with another lab, that they're also using the same type of geometry, because if not, you're going to get different values.
Yeah. And based on the industry you're in, they've standardized on specific geometries as well, or maybe not standardized, but preferred. Is that right?
Right.
Okay. Cool. That answer your question, Larry? Another question here. Do you find challenges when optical brighteners or neons, fluorescents are in a sample?
I would say challenges, but yes, we do find some different things like fluorescence becoming part of that calculation. So now you're adding a fluorescent factor. And one of our newer instruments, the Spectra 2 guide, that includes fluorescent measurement. And so it can take into account whatever that wavelength is that the fluorescence is hitting and give you the correct values.
Yeah.
But what you have to know is that over time, any type of fluorescent object is going to degrade. That's a challenge that you have with these different optical brighteners and neons, is over time that neon or that fluorescence is going to degrade and eventually go into a non-fluorescent color.
Yeah. And is that just almost like weathering, or does the...
Yeah, it's just a form of weathering. If you ever seen a fire engine, on the road, it's a bright red, but over time, if they don't take care of it, if they don't wax it and get it repainted, in 10 years, it might slowly degrade into a non-bright red, or it's going to degrade.
Just weathering, sun, rain, snow, whatever, in addition to just time degrading it. Okay.
Yeah. And what's interesting is there's no way to predict how when it will change, but there is some technology out there that can predict how it's going to change. So what it's going to look like when it has zero fluorescence.
Gotcha. So they can take So let me just get this right. So if you have something with fluorescence, there's technology out there that will, anticipate what it'll look like, if as it starts losing that fluorescence all the way down to zero fluorescence. Is that right?
Right. So in our software, I mentioned one of our instruments measures fluorescence.
Yeah.
In our software, there's a slider and a graph, and it'll show you, right now this color has, X amount of fluorescence. And you can slide that slider down to when it has zero reflectance and see what those values are going to be.
Ah, cool. Cool. We'll have to do a little video clip or demonstration of you showing that software, because I think that's a cool feature that I didn't even know was in there. Not that I play with it every day, so I'll mark that down. Let's see. Okay, so these color spaces have to do with additive colors. Do they work the same with subtractive colors? Can you talk more about additive color, light versus subtractive colors, like printing inks? Let me read that again.
Yeah, go ahead and read that again.
Okay. So these color spaces have to do with additive colors. Do they work the same with subtractive colors? Can you talk more about additive color, light versus subtractive colors, like printing inks? Hey, Larry, would you mind if I unlocked your microphone? Do you mind elaborating a little bit? You should now be able to unmute yourself. There's a button in the upper right-hand corner, like a little red microphone. If you're able to, feel free to unmute yourself.
Yeah, could you hear me?
Yeah. Yep. Hey, Larry.
Okay. Hi. Good.
A new voice. I get tired of hearing myself and Noah. So welcome.
Thank you, man. This is a great presentation, because this is something that's hard to get a lot of info out there.
Yeah.
On it, but I was just reading up about additive color versus subtractive, and how light is additive color, and like printing inks is more, I guess, subtractive. I don't know, I might have it backwards, where you'll see on maybe for a color printer, you'll see colors like they'll have, instead of having the RGB, they have the, I think it's yellow, cyan, and I forget the other color, but it's different. So yeah, I don't know if that's something that you could elaborate on, or it may not be proper for this.
No. Right. Yeah, I'd have to say I'm not too familiar with the the RGB and those types of color scales. I'm mostly focused on this type of color space for color measurement over different industries. But that is something to I'll definitely research about the subtractive and additives.
Yeah,
it's interesting.
I just did some search in here, additive versus subtractive color. This is basically, these are two methods for producing color or creating color. Additive color is primarily when shades of light are used to create colors, while the subtractive mode is used when you have your white light, such as sunlight, reflecting off an object. So that it does get into the additive, primary colors being RGB, and the subtractive primary colors being your CMYK. So I again, I'm not the expert, but from being in marketing and the print side of things, it looks like the subtractive primaries are, you have right being printing inks, because you're in a CMYK realm, as opposed to RGB, where you're looking, at a screen or your iPhone or something, like that. So I think you have it right, but I don't know. This is I've been around the color stuff for a while, and this is a new term for me. I don't think we've really had to address it when we're dealing with spectrophotometry or fluorescence or just color measurement or QC. at all. But yeah, another one, Noah. This is, we can look into this together and develop a white paper on this. If this is something new that's out there, or a new term, we can outline that.
Yeah, absolutely.
Oh, we got Megan chimed in here too. Additive colors are light and can be used for things like LEDs or like in your computer screen when lights are all on, your screen is white. Subtractive colors are better understood as the reflective colors from an object like paper with print colors. So, okay, we're talking the same thing. So thank you for the input, Megan. See, we learn too. It's always good. And if, there's a challenge or something that you're experiencing that we can't or don't know the answer, we'll find out, what it is and do the research and do the testing. As always, if you have some materials that need some testing, we can hook you up with Noah and, he can run some tests for you. We have regional sales reps and technical specialists around not just the country, the US and Canada, but also around the globe. So we can help you. Larry, does that help? Any other, or did you things more?
No, it does. I think it has to do more with how color is created.
Yeah,
you create it by light, and then others, by printing or by pigments.
Yeah.
But when you try and explain it to folks in a meeting, it gets in, when you try to tell them that, the color black is really the absence of color,
right?
And white is all the color. You start getting into some real philosophical kind of stuff that they can't wrap their heads around, So
yep, exactly.
I just wanted to touch on that and just see if you guys had any info on it. So
yeah, no, we appreciate it. Well, I'll add it to my list and hit Noah up, and we'll start diving into this a bit more. But yeah, I think you're right. It's the creation of color as opposed to measuring what's already produced or during production.
Yeah. So I didn't know if it had anything to do with how it's measured, if that factors in at all. So
yeah, gotcha.
But thank you.
You bet. You're welcome. Other questions or comments out there from anyone? This has been a good discussion, from everyone. Also, like I said, you'll get an automated marketing message with the recording of this, as well as this discussion. If you have any questions later today or next week or down the road, you can always just hit reply to any of these marketing messages. It'll come to my team, and we'll route you to the right technical expert or the regional sales rep in your area. If they need to come in and, do a demo or dig into your color program or go from there. Got a little bit of time left. We can give it a few more minutes. Any parting words of wisdom when it comes to color equations, Noah?
Absolutely. So if you're ever thinking of, changing your color equation, first I would recommend to look into what your industry standards are. Ask around different people in your industry and see if that's a great idea, because, you could have some issues down the line where, stuff doesn't match right. So definitely look into what your industry standards are, and then look into what competitors are doing, figure out if, they're using one equation or another and why. There could be a reason behind that.
Yeah.
But overall, Delta E 2000, the most current recent equation, is by far one of the most accurate ones at this point in time.
Good. Until they develop something else, huh?
Yeah, exactly. Until someone comes up with something better. For now, this is one of the most accurate ones.
Good. Hey, and that brings a question too. If you're looking to change your color equation, if you have all kinds of historical data, would a software package convert all those, or is it essentially wiping the slate clean and starting fresh? I mean, how big of a hassle is that? Because I assume there has to be a good reason if you're looking to change a color equation.
Right. So that reason would be if you have new colors that you're developing, and you need to find these tolerances, instead of having someone sit down with 100 different panels and set the tolerancing for that.
Yeah.
It's a long and time-consuming process. It would be better to just have this, transfer everything to a new equation and use equipment and software to just mathematically change, your old values to your new values.
Got it. So, okay, may not be as big of a hassle as I thought. Okay. That's good. Modern technology, gotta love it. Got a couple more questions. This is great. Is the color gray does it run more along the L axis, close to 0, AB?
Yes, so it does run along the L axis. I'd say it's around 50. 50, the value of 50 on the L axis. But yeah, it lies pretty much in the center of the A and B axis.
Okay, directly between that black and the white, you're going to get a good solid medium gray. And
right,
if you tilt it either way, you're going lighter or darker.
Yep.
Cool. Another one, when you say Delta E2000 is the most accurate, do you mean it gets the closest to human perception of color differences?
Yes, that's right. So, you have to remember our eyes are not perfect.
Yeah.
But what we're trying to do is create math equations that can correlate to what our eyes see. So it's, if you really think about it, it's almost an impossible task, especially because everybody's eyes are different. Your eyes aren't like machines. They're not exactly the same and perfect.
Yeah.
But yeah, as of right now, Delta E2000 matches the closest to our visual perception.
And then when you're using the instrumentation, that eliminates any differences in the human eye from person to person, because that
Exactly.
it's known females can see color better than males. The older you get to, the more challenges you may have. And I know we have the was it Farnsworth Munsell hue test that's out there. I took that years ago, and I have trouble seeing the blues and the purples in that range of things, and it's just the way I physically see. So I think if you haven't taken that, if you're doing visual analysis, it might be a good idea to get that checked to see how accurate you are. Your eye is physically at seeing color. Paired with the instrumentation, that's going to take that human element out of it. But I know, here at BIC, we always believe in a good instrumentation and visual color analysis, when you're looking at things. So there you go. I think that wraps it up. That's all of our questions. Yeah, like I said, you'll get the recording. If something comes up, feel free to reach out to us or hit reply to that automated marketing message. We got a couple more office hours in November. You'll get I don't remember the topic in November, but I know I think the second week of December, we kind of have our year-end wrap up, that it's really, no shortened presentation. It's just kind of an open forum for discussion to solve problems. Anything on your mind when it comes to color appearance or physical testing. We'll make sure a lot of our regional sales folks and business line managers are on the line too. So a couple more office hours coming up, and probably pretty quickly we'll start looking at the 2024 calendar. So, again, that's an opportunity. If there's something you want to see, if there's something you want to learn about, I can work with Noah, and we can definitely put together a program and run an office hours or a longer presentation if needed. So again, if you have any topic ideas, things that are, been bugging you and, you need some answers on, you can just hit reply to those marketing messages, and, we'll get it and go from there. And then we can put together a program and incorporate it into the 2024 schedule. It's kind of crazy. We're thinking 2024 already, but man, it's coming fast. So anyway, I'll quit rambling. Thank you for everyone who attended. Hope you learned something. I always do at these. Noah, thank you very much for sharing your expertise and answering questions. And we look forward to seeing you on future Bic Gardner web seminars. So thanks and have a great day, everyone.